let me just start this. There's quite a lot of material here, so I'll start unless there are any questions at this point. So basically where we are is we have structured the process so that it is well behaved. It has to be in an equilibrium, which we call stationarity, spatial stationarity. And for practical purposes, we turn this into constraints on the moments of the distribution, the mean, the variance, and the covariance. Basically, making them location invariant. Where you observe these doesn't matter. Okay. The variogram, or the semi-variogram, and I'll explain in a few minutes the distinction between them, which is very important. Some people get totally bent out of shape when you call a variogram a semi-variogram and vice versa. So it's important that you know which is which. The variogram is a kind of a weird statistic. It's a second-order statistic. And in order for that to work, of course, you have to assume the first moment away, which we do by this assumption of no spatial trend. And this is referred to in the literature as the intrinsic hypothesis. It's actually less restrictive than working with covariances, as we'll see in a few minutes. So all we're assuming now is that there is no spatial trend, so constant mean. The variance is constant. And then we're assuming something about how variables co-vary with different locations. But it's not the usual cross product, and covariance is a cross product, but it's a difference. And that's the different take that geostatistics, the way geostatistics approaches spatial data. As we'll see, in the end, it doesn't really matter because there are just two ways of looking at the same thing, and they are ultimately connected. So ultimately, we will be able to go from the semi-variance to the variance and the covariance and vice versa. But the point of departure in geostatistics is this weird thing, which is the variance of the first difference at different locations. So what is the difference between ZS plus H and ZS on average? Come on. 0, right? Because on average, the expected value is that they're the same everywhere. So if they're the same everywhere, then on average, their difference will be 0. So that average difference is not interesting. What is interesting is how does the variability around that average difference. Remember, it's 0 on average, but it's not always 0. Those are not the same thing. So you can have 0 on average with as an average of -1 and +1, or you can have 0 on average as an average of -100 and +100. It's the same average. In the first case, the variability around it is much smaller than in the second case. And that is the concept that we're looking at here, is the variability around the difference of two random variables taken at locations that are a given displacement h apart. And in the slides that follow, we'll use this h thing. In theory, h is both distance and angle, okay, and direction. In practice, we'll mostly just use distance. But you have to keep in mind that the strict requirement is not only distance, it's both distance and direction. And later we'll see directional variograms, for example, that take that into account. So what we're focusing on is the variability of this difference between two random variables, a given displacement from each other. And what we will want to see is some relationship between this variability and our h, our displacement. Specifically, what we will want to see is that this variability increases as locations get further and further apart. This is just an illustration of how you get from a variability in a process to something that no longer has a variability. And so we take a simple first order trend surface on these Baltimore prices, and so after we fit that through the data, the difference between that surface and the observed prices are the residuals. And they, by construction, have mean zero. So obviously, the prices themselves don't have a mean that is constant, because there is a slope here. These slopes are not zero. If the slopes were zero, then the price would have a constant mean. Okay? If the surface that you fit through the prices of this city is flat, that means that on average the price is the same everywhere. Since it's not flat, it goes down in the east direction and it goes up in the north direction. So there's variability in there. That violates our assumption of a constant mean. How do we get to the constant mean? We take out the predicted value from the trend surface, the residuals have mean zero, and we're back in business. So that's how this works. The semi-variogram, as yes, Bill. You came in late, so.
I know. But I don't understand, and you probably said it before.
I did.
If we're constant over space, that's what we learned exactly. We're looking for the
Well, what we're learning is nothing about the mean, but we're learning about the second order moments, which are specifically the spatial correlation between the residuals. So we're interested in, if it makes it easier for you, we're interested in residuals that have a mean of zero and have a constant variance, but they're spatially correlated.
This is the beginning of what we're going to get into later, is spatial autocorrelation.
This is one form of spatial autocorrelation.
So spatial autocorrelation is always looking at the second order moment.
Yes. Spatial autocorrelation is another word for spatial not another word. It's related to the spatial covariance, and a covariance is a second order moment. So technically speaking, I should be talking about the variance covariance matrix. So that's both the variance and the covariances are together the second order moments. So the first order moment is not interesting. It is interesting, but we've assumed it away by making it constant. Okay? The second order moment, the first part of it, we've also assumed away by making it constant. The variance has to be constant. And so we're only focusing on the other part, which is how random variables in different locations covary. Okay? The null hypothesis later is that they don't covary, but that's not interesting. So we're interested in situations where they do covary, and specifically, how do they covary? And we'll get back to this after the break. Any questions? Everybody's on board? So we're looking, no? We're looking at second order characteristics. Okay? We're trying to get at some way to quantify how things vary jointly given a function of how far apart they are. Okay, so this is where things get weird, but you'll see in the end it all makes sense. You see these two things. So 2 times gamma that's typically used for the semi-variogram is defined, this is a definition, is the variance of the difference between 2 random variables separated, let's just say, by distance h. So we want to, this is the example I gave of the -1 + 1 around 0, or -100 + 100 around 0. The variability around the average difference, given how far apart they are. Now, this variance as such is called the variogram. Half of it is called the semi-variogram. Now, this is important. You may think, yeah, well, I'm just making life complicated. It's important because, and just running ahead, the connection between this variance of the difference and the traditional variance and covariance is made at the level of the semi-variogram. We'll see that the semi-variogram, gamma at h, is the variance of the process minus the covariance for distance h. So the semi-variogram is half the variogram. And as long as you remember that, the literature is not totally consistent. And as I mentioned, some people get totally bent out of shape about this. And you can get a sense of that from looking at some of the text references that I gave you. But just as long as you remember, you start with the variogram, which is the variance, and then the semi-variogram is half of that variance. So because we're starting with the variance, but because we have the constant mean assumption, as we just saw before the break, the average of this difference, since they are both the same, is 0, so that the variance of the difference boils down to being nothing but an expected value of squared differences. The variance is the average difference between the random variable and its mean squared, right? Because the mean is 0, all we have to worry about is the square of the original random variable, which in this case is the difference between these two. So if we do have this constant mean assumption, then this variance of the differences is the same as the average squared difference. Average in the sense of expected value of the squared difference. And remember what I said the other day. Anytime we have expected values, we can turn them into averages, and that's great because we can compute averages. And so then we're in business because we can take our data, as long as we can figure out what these square differences are, we can take the average, and that is an estimate for the expected value, which is a characteristic of the spatial distribution. So to make things a little more complicated then, the semi-variogram, gamma h, is 1/2 of the expected value of the square differences of a random variable at distance h apart. Think about spatial autocorrelation. What does that mean? It means that things that are close by are more similar than things that are further away. So if we take a z at two locations that are close by, what will their square difference be? Will it be larger or smaller than two locations further away from each other? Smaller, because they're more similar. As they become more dissimilar, the square difference gets larger. So the semi-variogram is very small for locations that are very close together. In the limit, it's 0 for locations that are in the same spot. And it increases as the locations are further and further away from each other. So it's a characteristic, if you wish, of the dissimilarity between two locations given a distance, the distance that they are apart. The more apart, the more dissimilar. The closer, the less dissimilar. Or you can turn it around and say, the closer, the more similar. The further apart, the less similar. Okay? And those are two sides of the same coin. When we focus on dissimilarity, on square differences, we'll be dealing with variograms. When we talk about similarity, we'll talk about covariances, the traditional cross-product statistics. So the semi-variogram deals with square differences. The covariograph deals with cross products. That's the main difference. But they're both ways of characterizing the spatial autocorrelation in the process. This particular thing is called a variogram cloud plot, and we will use this as an exploratory device to focus on whether or not these assumptions that we've been making are legitimate assumptions for the data at hand. The variogram cloud plot is nothing but every single one of the square differences in our data set, not double counting. So if you have n points, how many are in here? N times n minus 1 over 2. Okay? Not the ones in the same spot, 0 and 0, that doesn't count. But we have all the square differences for all the pairs of observations. And on the horizontal axis, we have how far apart they are. On the vertical axis, we have the magnitude of the square difference. So what we would like to see is some overall tendency that they start small and they become larger as we move further away. Now you can't see this in here. You will have to simplify this, and we will simplify it to get a summary measure of the overall pattern in this cloud plot. What we use this for is to look for outliers. What would be an outlier would be two locations that are very close but have a large square difference. For example, you see here, these points have a much larger square difference than the bulk of the others for that difference apart. And then, with the right tools, and we'll see how to do this in geostatistical analysis, and with a little bit of work in R, we'll have the same result. You get something like this. This is not R, this is Variogram, but we'll do the same kind of operation in the other ones. And what we've done, or what you will do in the lab, is select these kind of points, because these are points with a much higher square difference than the bulk of the other ones for that distance. Now, keep in mind, every point in the variogram cloud is really about two observations. It's the square difference between two observations. So if you click on a point like that, it connects to two locations on the map, because it's the square difference between those two locations. So in some software, you can do this, and you select these points, and then it draws the lines that connect the pairs. Now, what's special about this particular case? So I have selected 3 points in the variogram cloud plot. Those are 3 points that correspond to pairs of observations. And what do we see when we map them? It's highlighted in red. They all have the same one in common. So one of these 3 points is this one and that one. Another one is this one again with a different one. And then this one again with a different one. That starts to suggest the notion of an outlier. Why an outlier? This red point is relatively close to these other points, but the square differences are much larger than they would be, if you followed the overall pattern. And that's what we're looking for. And there's a nice example in one of Cressy's papers where he's looking at something in New England, some environmental characteristic. And he has a variogram cloud plot in the paper, finds the outlier. It's something like this, and in fact in the lab you do something similar. It's a similar instance. And the pairs all connect to the same location. And then they found out that is a location where the monitoring station had a defect. And so it was actually measuring everything off by some magnitude. In the example that we'll see for Los Angeles Basin, it's not a defect, but it's a topological, it has to do with the topography. And Luis has a nice picture, and he will show you on Thursday. We can do it without the picture and draw the same conclusion, but once you see the picture, you will, well, I know, but once you see the picture, you will see what is going on. The lesson of this is that we can figure this out without seeing the picture. So from exploring the variogram cloud, we can identify potential outliers, potential observation points where something might be wrong, like in the case of the defect, or where our original assumption of stationarity, which is in so many words means the same process applies everywhere, really doesn't hold, because in some places there is a different process. In the case of LA, it is because we're on the other side of the mountain, as you'll see on Thursday. So how do we estimate this semi-variogram or variogram? Remember, the variogram is 2 times gamma. The semi-variogram is gamma. And I should warn you that in some software packages, the plots that come out show you gamma, even though what is calculated is actually 2 gamma. So you should look at the fine print. It doesn't really matter as long as you're consistent throughout, but typically what we do is switch between different packages, and then you better hope that they all use the same convention. Otherwise, everything will be double of what it should be. Okay? That's the price you pay. So remember, we have an expected value of the square differences. How can we estimate this? Well, we already know estimating expected values is taking an average. Now, an average of what? We could take our whole variogram cloud plot and take an average of all these square differences. That would give us one number. But what it wouldn't give us is a connection between that number and the distance that these points are apart. On the other hand, we cannot do this for every possible distance, because there again, we'd have 1 or 2 maybe by chance numbers of 2 pairs that happen to be exactly a given distance apart. So what we do is the next best thing. We group the distances in bins. Let's say 0 to 2, 2 to 4, 4 to 6, 6 to 10, to 8, and so on. Then in each of these bins, we have a collection of observation pairs that are a distance apart that falls within this tolerance between 0 and 2 miles, or between 2 and 4 miles apart. And then we take the average of those. However many there may be. And this however many there may be is this n of h number here. So that's the number of pairs that we actually have in the bin. So for that bin, we take all those square differences and we take the average of those for the bin. That average for the bin is the variogram estimate. Half of it is the semi-variogram estimate for that bin, and that's associated with a value of h. And we do this for different values of h, and the result is a variogram plot, something like this. We'll see several of these, and we'll see that it's actually not that easy in the lab, but that's the point of the lab. But the bottom line is very simple. We just cut it in bins. For each of these bins, we get the average. Now, what's the problem with this? Well, think of the Baltimore data set. As you in the core, there's a lot of houses that are fairly close together. But as you move further away, there are not equally many houses that are longer distances apart. So what you get is a thinning. As the distances get larger and larger, fewer and fewer of your sample points are that far apart. So whereas, say, for the shorter distances, you might easily have, 100, 150 points, pairs of points on which you compute that average. As you get to 20 miles apart, 30 miles apart, you may have 2 or 3. And that's not reliable. Remember, an average is just an estimate. And there is such a thing as the precision of that estimate. And the precision of that estimate is related to how many points you include, pairs of points you include in the average. So the more pairs you have in the average, the more precise your estimate of the average will be. Okay? 2 problems here. One is, if you don't have enough points in there, your estimate of the average will be pretty worthless, because it will be so imprecise you might as well not do it. So typically, that's also what happens. You cut off and you say, beyond this distance, I'm just not going to bother, because these additional averages really won't tell me anything about the process. And that is called the distance of reliability. The rule of thumb, but that's all it is. There's no statistics here. The rule of thumb is that you take half of the maximum distance in the point pattern, if you wish. So you take all the possible pairs and you compute the largest distance that they're apart. Then you take half of that, and that is where you stop. So for pairs that are further apart than that distance, you don't bother computing the average. Okay? So that's one thing. There's not enough pairs. The second aspect is that the number of these pairs in each bin is not constant. As a result, the precision of your estimate in each of the bins will be different. So even though you're looking at these points as if they are exact, in fact, they're not. And if you would draw, like we did with the envelope, draw a range around them, for some of these the range would be narrow, for others it would be wider. The bottom line is it's not the same. This is a heteroscedastic estimate, which later on we'll need to take into account when we try to estimate processes, because the precision in each of these bins is going to be different. To get back to my story about GStat, in GStat, the distance of reliability is 1/3 of the diagonal of the bounding box of the points. Okay. This is in the notes, so you know what it is. It is not half the maximum distance. Now, geostatistics is a very practical field. It's big in engineering. Engineers are very practical people. They often don't have a lot of patience with theory. So they use these rules of thumb that have some connection to theory, but they're just practical things. So one of the things we will be doing in the lab is really seeing how much of a difference it makes. Where do you cut this off? The principle, the statistical principle that underlies this cutting off is that you need to have sufficient observations to have a reliable estimate of the mean. That is the bottom line. So there's another rule of thumb which you probably all have heard of, this magical number 30, is that you should have at least 30 pairs in each of these bins, or again, these estimates won't be very reliable. So between these two rules of thumb, we're now in business. We have observations at a sample of points. We take the square differences, we sort them by distance, we put them in distance bins, and we compute the average in each of these bins. We take half of that, that's the semi-variogram. And that's the estimate. So the semi-variogram is actually not a line. It's very confusing because several textbooks show you these lines which are theoretical semi-variograms. But the empirical ones are not lines, they're points. They're point estimates, one for each bin. Okay, the two other pieces are the covariogram and the correlogram. So the semi-variogram or the variogram dealt with square differences. The covariogram is very confusing. They all have vario in them, but they're really different concepts. The covariogram has to do with covariances, which are cross products. Okay. So again, we need stationarity here, which translates into that the covariogram, the covariance, has to be regular over space, meaning it should not depend on the location, but only on the separation. That's the same as what we had before. But now the constraint pertains to the cross product, not to the square difference. Now, what's the difference? How would you differentiate the cross product from the square difference in terms of statistical requirements? Think about this for a second. the square difference does not include something that the cross product does include. And we've actually already taken advantage of it. When you take the difference of two random variables, the mean gets washed out. So the square difference, the mean is gone. When you take a cross product, you multiply them together, the mean is still in there. So the covariances are about cross products. And to have these cross products to be regular, we actually need to assume more about the process than with the square differences. With the square differences, as long as the mean is the same, we're in business. We don't have to know what that mean is. Here we do, because the cross products depend on the level, if you wish. Okay? So it's a little stronger assumption. But the covariance is just a covariance. Covariance is just the expected value of the cross product of two random variables. What are our two random variables in this case? They are the same z, but measured at distance h apart, or separation h apart. So we will index the covariance by the distance that the two observations are apart. And then, by definition, if we make that h equals 0, we have the covariance between z at s and z at s, which is the same as the variance at s. So c at 0 is the variance of the process. C at h is the covariance of the process. How the random variables co-vary as you look at them a given distance apart. Okay. The variance is simply how they vary around their mean value. Covariance has to do with different locations. Variance is the same location. When we have the covariance indexed by distance, and we have the variance of the process, then we define the correlation, if you wish, just like we get the regular correlation as a covariance divided by the standard deviation of the first variable times the standard deviation of the second variable. Here, because this it's the same variable, so you multiply the standard deviation with the other one, that's the same as the variance. So the covariance divided by the variance, the C of h divided by the C of 0, is called the autocorrelation function, or in the literature called the correlogram. This is a correlation function that shows you how a random variable is correlated with another random variable a given distance away from it. And so, using Tobler, we know the correlation will start high. In fact, it starts at 1 for distance 0, because at distance 0, CH is C0, so the ratio of these two is 1. And then it goes down as you move away further and further apart. So we have now 3 concepts. Well, 4, if you count the variance. We have the variogram and the semi-variogram, which are related how squared differences change with distance. We have the variogram, the covariogram, that's the second one, which tells us how covariances, cross products, change with distance. And we have the correlogram, which is the covariogram with the scale taken out. And that is like a correlation. The largest value you can have is 1. And everything is standardized with respect to 1. These 3 things are just different ways of describing the same process. And they are in fact related. So this is a correlogram. You see in practice there's just points. There's not a line. And then from these points you have to figure out, as we did before, what is the process that drives this. This is the relation that ties everything together. So it's a little bit of algebra, but it's not difficult algebra. So we start with the definition of the variogram. So So the variogram being 2 times gamma, which is the expected value of the square differences of the random variable z, distance h apart. So what the algebra that we'll be doing is just working out what this is. So this is the square differences. Square of difference is the square of this one plus the square of that one minus twice the cross product of the two. Right? That's algebra. You're with me, right? So because we have a constant mean assumption and a constant variance assumption, the square of this one and the square of that one is the same. It's simply the variance of the process. And here we have minus 2 times the covariance. So now this is where the magic 2 comes into play, because if we divide both sides by 2, we get that the semi-variogram, which comes from the square differences, equals the variance of the process minus the covariance for distance h. Covariance being a cross product. So this connects the square differences to the cross product through the variance of the process. Now, why would you want to do this? Statisticians and models don't like to work with square differences. They like to work with covariances. Now, in some cases, in many practical cases, it's easier to estimate this than it is to estimate that. And why is it easier? I just mentioned it. Because you don't need to know the mean. You don't need to estimate the mean. So that's easy. But because of this connection, this relation, you can always move from one to the other. So with an estimate of the semi-variogram in hand, given the variance of the process, you can compute the covariance for that same distance, and vice versa. But typically, and the reason why this came about, is that it's a lot easier in many circumstances to estimate the semi-variogram than it is to estimate the covariance of a process.